I don't know. I think I dropped out for a second.
Welcome. Welcome everyone. Together with Shreshth Tuli, I'm pleased to welcome you to this tutorial. My name is Giuliano Casale. Both myself and Shreshth work at Imperial College London. And today, as you know, we would like to discuss with you certain techniques that are emerging to do scheduling and management in the context of fog computing, which is a recent trend that brings together edge computing and cloud computing. And so I like to start first of all by showing you the agenda for this tutorial. So I will give an introduction to the core concepts and the ideas of the methods we will explain later on in more detail, in particular a technique called co-simulation that you will have a chance also to try hands-on later in the day. So after this introductory section, we will have a short break and then we will look at this co-simulation technique where we will introduce Costco, which is a software asset that you can find, software solution that you can find at this GitHub address you see here in the slide that allows you to do scheduling and dispatch work to fog resources with a high degree of automation. And you will be able to try it today later in the technical part 2. We will tell you a little bit more about the internals of Costco. If you have Python skills, it will be hopefully all easy to follow because we will go also in the code, but strictly speaking is not required to know Python. The code is quite self-explanatory if you know any programming language, and so you'll be able to code with us some lines of code to define a scheduler with Costco, and so then you will have the minimum toolkit to apply Costco in your problems. As I said, if you need to ask questions, just raise your hand or write in the chat on Slack. With this, then I will start the initial introduction. Perhaps before we get there, just a reminder that for the hands-on part, you will need with you your GitHub account credentials and a browser among Chrome, Edge, or Safari. So let's get started with this tutorial. There are, as I'm sure you know, a lot of interesting applications that are emerging and getting a lot of traction in industry nowadays related to autonomous driving or voice-controlled assistance. But also mobile applications that heavily leverage AI and machine learning for personalized healthcare, or smart home security applications, which allow you to control devices in your home that ensure security of the environment. And all these type of applications are arising in this time period, especially because deep learning have enabled the deployment of intelligence in the form of deep neural networks in many applications, including the ones I'm showing here. And of course, there are also developments in terms of resource management in cloud and edge computing, and also in networking, for example, with 5G, that are making it possible to deliver the expected latency and performance in these vertical application domains. And so if you have to engineer this kind of applications, there are many concerns. So in addition to latency, you might be interested to the, say, energy and sustainability angle, or the privacy of data, or the accuracy of the neural networks that are deployed in this type of applications. We will center our attention in particular on latency, but also a little bit on energy when it comes to this tutorial. And in terms of, say, edge and fog computing resources, I would like to give you a few basic notions. So we will look at throughout the tutorial to QoS management in fog computing. So as I said, latency is important, and I will say that the requirements very often in this domain are ultra low latency requirements. So you want these systems to be highly responsive. Obviously, if you are looking to a self-driving vehicle, you need to be able to process the inputs from the vehicle as fast as possible. And there are also aspects in the deployment of these applications that relate to the fact that each of these applications may be tailored in a slightly different way to different users. So you need essentially to customize the management on, say, individual needs. And therefore, this becomes very challenging because you might have very many instances of this application running concurrently on your infrastructure. Your fog infrastructure typically consists of a cloud data center backend, edge devices in the physical environment, and brokers that connect these backends to the devices, and therefore that can help in managing data and services closer to the edge, and therefore with lower latency than if you would be doing this straight away from the cloud backend. And so there is this tension between the edge and the cloud backend in the fact that you would like to stay with the processing as close as possible to the edge, so that the, say, data travel times transfer times are reduced. But at the edge, the processing capacity that you have to process the data is typically much less than the processing capacity that you have in a cloud backend. So there is a trade-off here between the power and the processing power and the latency that is experienced by the end users. And so this is a complex type of infrastructure to run applications, and therefore management is quite challenging. There are also very many devices of different types. They are heterogeneous in terms of capacities and characteristics, and this is a further element of complexity in the management. So with this complexity and the scale and the, say, tailoring of the solutions to say, customize the needs, it is clear that you need a high degree of automation. And there is a perception in industry that only AI and machine learning methods can deliver the required accuracy and speed to manage resources in these cloud to edge fog architectures. So we will talk about these methods today. And I would like to mention briefly that Because of this increasing need for automation in this domain, we see also a resurgence, even in research, of investigations on self-adaptivity and self-management techniques. They have received a lot of attention around 10 years ago, when the first works on autonomic systems came out, especially in the software engineering community. And today they are again of very broad interest to the research community and the practitioners, due to the need of combining these self-adaptation methods with AI and machine learning techniques to be able to have that these platforms can run reliably at all times in a say automated way. Otherwise, the cost involved in the management would be too large. And as I said, there are many complications due to heterogeneity and other inherent characteristics of the domain, but there are also challenges that relate actually to the complexity of the software that runs on this fog infrastructure. Let's try to see this with an example. What you see here is a call chain for a microservices-based architecture. So every horizontal bar here represents a thread. Different threads might be running on different resources across your infrastructure, and those that are indicated with the same color belong to the same microservice. So here, for example, you have 8 gray bars that indicate 8 threads of the same microservice. And this graph that you see highlighted here, so these are the microservices, and for example, the first one is the client, and the graph you see here describes the call chain, the results when there is initially a service invocation from the client to one or more microservices that then propagates in terms of a call chain throughout this type of architectures. And therefore, you see that there is inherent complexity in the structure of the call chain, which is even worsened when you reason on the fact that the context of the call can fork, can join, you can have parallelism, and therefore also contention in terms of queuing at the resources. And so being able to understand all this complexity is very difficult for a human, but still you need to have a way to capture this complexity in the management methods, because you want to change the configuration of the resources and of the software, which ultimately affects this behavior described in these slides. And how do we do this kind of management work, for example, in a community like ICP? Well, one of the say the historical techniques adopted by this community involves describing this kind of graphs by means of some model, for example, a layered queuing network, which is the class of models you see described here, where each parallelogram, the large parallelograms, represent a microservice, and the smaller parallelograms represent endpoints that can be invoked of those microservices. And so you come up with a modeling of these call graphs in terms of these, say, diagrams that allow subsequently to generate automatically performance models like queuing network models that you might use to do performance analysis or performance prediction. Indeed, these endpoints need to be first annotated with, for example, execution times of those calls, average execution times, also called resource demands. But given that you're able to do this for monitoring data, then you can generate performance predictions using this type of models. And therefore, one of the consequences is that you can also bring models of this kind runtime. You have a controller for your application that keeps this kind of representation based on model at all times. The model is synchronized to the data on the fly using monitoring information, and then you do performance management that way. So for example, in this slide you see here, you see on the left say inbound time series for the traffic that is inbound to the service. And so what you see here are the interval times between calls to an endpoint, and then you could characterize these statistically in terms of moments and, for example, autocorrelation function. Then you run some algorithm that fits your autocorrelation function and moments to some statistical model. And for example, some Markovian model. And once you have these parameters fitted on the data, you can use them to control, for example, CPU shares or auto-scale your application. And this is the classic way we have been doing things in a community like ICP or generally in performance evaluation. But now there is this new trend of using instead AI and machine learning methods. So I would like to do with you a walkthrough of the reasoning behind adopting these methods and what opportunities there are and what are the architectures that we could exploit for this. So in particular, I will discuss the problems within the broader management that deal with intelligent task scheduling, where you have tasks that are, say, standalone piece of work. They don't have dependencies among themselves. And you want to dispatch them to servers or workers, possibly running on different hosts, that can process these tasks. And actually, we will focus on the scenario where time is discretized, and therefore you might collect for a period of time some tasks, and then you want to dispatch this group of tasks to the different hosts. This is one setting for scheduling, but there are also more complex scheduling settings that we will also discuss that deal with workflows, where you have parallelism, but also precedences. And so you cannot start certain tasks until the precedences have been met, which means that certain other tasks must have completed before. And then I will spend a couple of slides to illustrate an application to the kind of software systems we discussed at the beginning, so edge AI applications like, for example, autonomous driving or this type of emerging applications. So let's get started, therefore, with first describing scheduling in general. So as I said, we want to schedule units of work on resources, and typically we want to do so in order to meet the quality of service objectives and also minimize costs, for example, by using as few hosts or resources as we can in case we are in light load. But scheduling is very well understood to be a difficult problem. Even in terms of computational complexity, very simple problems like load balancing can be shown to be NP hard, and therefore you don't have in general algorithms that will work to optimality for all the instances. And there are state-of-the-art methods, most of which come from the theory community, computer science theory community, such as bin packing, first fit or best fit decreasing heuristics that are commonly used in applications because they're very fast, being heuristics, and therefore can provide quite often formal guarantees on the, say, the gap between the optimal algorithm and the solution they provide as an approximation. So you have a certain guarantee that the solution they offer will be not worse than a certain percent compared to the optimum, even if the optimum is not known. And these methods, however, they're not very tight in terms of optimality. They leave a lot of margin for improvement. And therefore, there are other heuristics that have been studied over the years that perhaps don't come with guarantees. They are more practical. They deal also with things like migration that might be difficult to model in those simpler theoretical heuristics, and therefore they offer additional flexibility. However, these methods very often also can be inaccurate or far from optimality. Now, let's try to reason together on why we need in this context AI and machine learning methods. There are situations where you want to keep, like in this application workloads, very low latency. And therefore, you might, for example, want to do interference analysis in an environment. You want to study, for example, signals in an environment. You might want to do autonomous driving control. There may be a lot of scenarios where you need to react extremely fast. And if you use the models that we were considering before, like queuing models to control these applications, there are some difficulties that arise because once you operate those models at short time scales, you will have that they become essentially inaccurate. So if you look, for example, at the utilization of a resource over time, you sample every few seconds the state of a resource, and you try to reason on that state of the resource to be able to predict the latency that the tasks are going to experience at that resource. So what you do normally with the performance models, like the queuing models, is that you have relationships that connect metrics like utilization to observe the latency, and therefore your model gives you this connection, this mapping that allows you to predict the latencies. The problem is that when there are shorter time scales, the classic models typically do not follow very well the time varying behavior that you observe in the trace. They tend to smooth fluctuations because they have been derived analytically, taking long-term equilibrium assumptions that are not meant to capture these fluctuations at short time scales, and therefore they tend to be fairly inaccurate and unable to follow the continuous variations that you see in the data for latency, utilization, and so forth. And so this is the main difference, I would say, in terms of, say, performance between neural network-based methods and the traditional stochastic model, that neural network-based methods do not have a problem with operating at shorter time scales, and so they can return a low mean square errors even if you work at this type of time scales, or even shorter than 5 seconds. And so this is an important reason. There are others, like, for example, general accuracy can still be higher with AI machine learning methods than with traditional methods, even in longer time scales. But this gives you an intuition on why we really need to look at neural networks due to this time scale aspect. There are very many methods that we can use in AI machine learning to deal with, say, management. We will focus in this presentation primarily on two types of AI machine learning methods: surrogate models and deep neural networks. The others have received attention in the scientific literature, but we will not cover them too much to this presentation, only say marginally in the second part, some of them. So just to give you a sense of what are surrogate models, you will see this better in the next part, but they are essentially approximations of any metric you might study. You might look, for example, at Gaussian processes or other, say, flexible models that allow you to capture the dependence between the configuration of a system and its observed performance or energy consumption, or the state of the system and its observed performance or energy consumption. So you can fit from data very complex mappings and use these surrogate models, therefore, to approximate the response of a system. And one great properties they have is that they're very easy to update, and therefore, if you collect more data during operation, you can update these surfaces on the go. However, it's not clear how we should use these surrogate models concretely in a, say, in a performance management architecture, because we could use it in combination with a simulator, offline, online, standalone. So there are many combinations. So we will see now a few patterns. And I will start with, say, perhaps the simplest pattern, which is the idea that you are conducting a QoS say analysis or prediction study. Maybe you want to configure the first deployment of an application. And then what you do is that you run your simulator-based model or analytical model with very many combinations of parameters to build the surrogate surface that describes the way the system responds to these changes in configuration. And then you can essentially use an optimization algorithm, like, for example, an evolutionary method like genetic algorithms or CMA-ES, to search the best configuration using the surrogate surface to describe either the objective function of your search and or the constraints of your optimization problem. So when you evaluate in a constraint, for example, the latency, and you ask it shouldn't exceed a certain service level agreement threshold, then that evaluation could be done by evaluating a surrogate model. And so this kind of work is quite say, important for offline studies, but it has a difficulty when it comes to online or real-time control, as we need in fog computing, because they are very slow to run these methods based on optimization. And so another approach where you can embed the surrogate models in, say, runtime control, so could be then to apply a methodology similar to the one we do classically with the, say, stochastic models that you keep at runtime to configure your system. But what you do is that you could consider hybrid models, where some parts of your model are based on surrogate machine learning based response surfaces, instead of being, say, based on analytical models. So you come to the idea that if your model describes a distributed architecture, then there could be some blocks in this architecture that you model using, for example, say a mixer density network or a GAN that describes the latency of that component alone, whereas for the other components, you might use an analytical model. And this means that you can adapt the model based on data for some components at runtime using the surrogate approach. And also, in some cases, you can also be more accurate or faster in solving this model at runtime. Now, the main limitation of this kind of approach is that still you are not entirely general, in the sense that the model needs to live by the rule of the formalism that you use for the stochastic model part, right? If you tell me that a block exposes certain parameters, certain metrics, in order to plug in a block that is machine learning based that interacts with the others on the basis of those metrics, you are constrained to focus on those metrics. And so it might introduce some restrictions on what you can do with, in terms of generality in the model, even though you're using AI machine learning. And therefore, you might think at the point that perhaps we should just get out of the way the stochastic models or the simulation and just go for a neural network, right? We describe our system at runtime using a neural network. We will see this extensively in the next section. And therefore, you just update this neural network based surrogate model at runtime, and you have some fast algorithm to conduct optimization or choose how to change the configuration of the system based on this fast surface here, so fast sampling of the surface. And now you could do this, and it works in many cases, but one issue is that you are really essentially fitting and perhaps even overfitting the data based on what you are observing. You're not exploring other scenarios different from the data that you are receiving to update your neural network. And so you might not be able to predict efficiently all the options that are available in terms of decision making. And also there may be the case where your surrogate is evaluated at a configuration or say a pointer that is not very accurate because you haven't sampled a lot of data around that configuration or state. And so it might be the case that you have also a low fidelity reading from that surrogate. And so you might ask, how can I do better than this to cope with these issues? What we are going to discuss today extensively is the idea that these surrogate models could be coupled in the runtime environment with a simulator that is fed the readings from these surrogate surfaces, in particular to say generate candidate scheduling decisions. We will see this more later. And then based on this candidate scheduling decision, you could simulate the possible trajectory in the future for this small set of possible outcomes. And then, so the co-simulator is essentially a simulator that lives alongside your application that you use to predict in the future the evolution of the state of the system. But then what perhaps is less obvious is that there is intrinsic value at this point to couple with the simulation a second neural network that is able to essentially reconcile the differences in predictions between the original surrogate and what the simulation is telling us instead about the evolution of the system. So that progressively, the second neural network is able to compensate the errors that the first neural network is doing on the basis of the additional information that is provided by the simulator. And so you are still then able to work with a surrogate surface here in the second neural network, but that is informed through these two channels and therefore tends to be way more accurate than using just one of the two within the time constraints for this kind of fast scheduling decisions. And so we call Gobi and Gobi star the algorithms that we use to do this kind of controller runtime that will be described in more details later. And so to recap, you generate tentative scattering decisions with the first neural network, then you do the exploration of the consequences with the simulator, and then you can use the last neural network to compensate for the biases of the first surrogate. And so this could be a simulator in the middle, could be also an analytical model. And so we will see later certain results that corroborate the claim I'm making that this combination is more accurate. And so I would like to close this section with a quick example on how we can apply these notions of co-simulation to a real-world application of the kind we discussed at the beginning, so deep learning based enterprise applications. In particular, we often call these edge AI because they rely on sensing at the edge many of these applications. So what is the challenge in the applications we were discussing in this group? Well, the issue is that, as I said, there is a tension between processing at the edge and processing data at the big end in terms of say resources that are available for the processing versus latency that is experienced by the users. And so there are very many ways that have been studied over the last few years to operate these neural networks in a fog environment. So you could run the deep neural network say at the edge broker level, or have it running in the device, but then it needs to be very lightweight if you run it, say, on a mobile phone. Or you could split the neural network between the edge broker and the device, or split it between the edge broker and, say, the cloud backend. So you can access more compute capacity, but there is a question then, how do I split a neural network? And this is a new dimension for performance engineering, where you need to reason on also the, say, the deployment of the parts of your neural network. So the way this problem has been tackled in many applications is based on essentially deploying most of the neural network in the cloud backend, and only a very shallow, so lightweight model in the edge devices or say mobile phones. And what you do is that you try to use various techniques to make the whole chain as lightweight as possible. So like you could quantize, so reduce the number of bits in the information you transmit from the edge to the backend. You could do some form of compression. Actually, you can use techniques very similar to JPEG compression between these chunks of the neural network. You could apply techniques like early exit that allow the neural network to take an early decision on certain inputs so that it doesn't need to traverse all the layers of the neural network, and therefore it's faster to execute. So there are all these strategies that are being actively investigated, but still they are not very good in terms of accuracy of the resulting neural network. There are heavy trade-offs that you incur with these methods. And so there isn't a final solution out there yet. Some proposals more recently have been looking at splitting neural networks and deploy them according to say two main styles. One is called the layer-wise splitting. So what you see here is the neural network with the different colors indicating different hosts that are, or resources that are running that part of your neural network. And so here, this neural network has been divided such that some layers are on resource one, so yellow resource, and there are other two resources running the other layers. And this is called layer-wise splitting. But what you could do alternative is to run in a resource all the layers, but just a subset of the neurons in each layer. And this is called semantic splitting. And the research has shown that there is a trade-off between the accuracy of the neural network and the, say, the latency that you incur according to the style you choose. And so in our work, we have shown that using scheduling based on co-simulation, it is possible to come up with a scheduling system, which we call split place, that applies surrogates co-simulation and also contextual bandits to reason on service level agreements in order to dynamically choose between these two splitting styles and therefore help the scheduling of tasks for this kind of applications. And our results indicate that this method is very flexible and essentially brings together the best of both worlds from these two kinds of splitting. And so this is just a high level, say, intuition that the techniques we're going to study in the next block can help you in concrete problems related to edge AI applications. But we will continue these in more details in the next part. So to recap on this section, we have learned that the AI machine learning methods offer a new way to tackle scheduling problems when there are latency sensitive workloads. Surrogate models are an essential ingredient for these controllers. And our claim is that techniques such as co-simulation that blend say, simulation-based or analytical models together with surrogates can deliver better results than using just either of the two. And therefore, there is essentially value both in investing effort in AI machine learning methods, but also evolving alongside the more traditional, say, simulation-based or analytical methods. So we will see this more in the next section, just a few hints of potential challenges in this space. One difficulty that these methods have is the cost of training and, say, the memory consumption of these AI machine learning methods. It could be high compared to, say, more lightweight analytical models. And there is research trying to lower the memory consumption at the edge for many AI machine learning methods. And so we expect that this kind of trend will lead progressively to allowing the use of more and more complex AI methods at the edge. There's also the fact that AI machine learning methods are trained on data that quite often is assumed to not to change dramatically if you have done, for example, a pre-trained of some components, you have done it on a set of traces, and therefore if the characteristics of the runtime workers are completely different from those traces, it is possible that there is a low performance for the AI machine learning method. So the ability to recognize discontinuities in the runtime data and, say, reset in the runtime environment the training and testing of the AI machine learning methods is still a work in progress in the area. With this, I stop here. Unless there are questions, we can take a short break at this stage. Any question? Feel free to unmute if you like. Okay. So if we don't have questions, then we can take perhaps a short break. We can take a 5 minutes break. And then we return with the second part that will be presented by Shreshth. Okay, so we'll be back at 51 past.
Okay, so thanks everyone for joining back. And first of all, this is the second part of the tutorial. I am Shreshth Tuli, and I'm a PhD student at the Department of Computing, Imperial College London. And this part of the tutorial covers, say, the topic of how to optimize the performance of fog computing environments using these AI and coupled simulation ideas that we also refer to as co-simulation that Giuliano described in the first part. And so let me quickly summarize before diving into the technical details, the system model assumptions that we use rest part of the talk. So just as what Giuliano described, we assume, say, a fog computing architecture, which is heterogeneous, and it has these nodes in a broker-worker fashion, which is, say, a typical case in most fog computing environments. We assume that the various resource utilization characteristics like CPU, RAM, network bandwidth, and disk capacities of each node are known in advance. And similarly, we can sample these resource consumption metrics for each task in the environment at any time. Moreover, we consider that the tasks include a batch of inputs that need to be processed by any host node. And further, for each task, there is a service level deadline that is defined at the time the task is sent to the system. And all tasks are received from this IoT layer, which includes sensors, actuators, to collect data from the users and send it across the fog broker via these gateway devices, which are like acting like an interface between the users or IoT devices and the fog infrastructure. So then the fog broker decides where to allocate these new tasks, where to migrate, if at all, the active tasks in the system, and say manage these resources effectively to, say, optimize quality of service or QoS parameters. So in terms of the workloads, we divide the timeline into equal duration intervals and create workload tasks at the beginning of each scheduling intervals using, say, a Poisson distribution. And this is similar to various discrete time control assumptions that are fairly common in this resource community, as well as performance engineering community, such as ICPE. And although our methods are agnostic to the specific QoS objectives, in this part of the tutorial, we will specifically focus on optimizing parameters such as latency, response time, average energy consumption, or maybe, say, some combination of these metrics. Okay, so let me now, say, give you an understanding based on the system model that we've discussed, give an understanding of what kind of ways we can generate these surrogate models that Giuliano described earlier in the tutorial. So there are several data-driven methods, specifically that rely on AI, machine learning, or deep learning models to solve the resource management problems in fog computing environments. And the fundamental core of most AI-based resource management solutions is based on this idea of deep learning, which uses this deep neural networks. So just briefly giving a background of what this neural network is and how we can use it to, say, solve problems related to optimization and resource management decision-making in fog environments. So as the name suggests, a neural network akin to, say, a cognitive brain constitutes of neurons, and each neuron takes two or more inputs, performs some elementary operation on those, such as, say, a simple dot product, and produces a single output. When we stack, say, multiple such neurons for the same set of inputs, we can generate multiple outputs, and this is called a layer of neurons. And when we stack these layers together, say, for sequential processing, we call these deep neural networks. And there are several types of neural networks, depending on what that neuron structure is, what kind of elementary operation it performs. And the simplest ones are variations of these, what is called feed-forward neural network, also called fully connected neural network in the literature. that simply performs a dot product with, say, a parameter weight and adds a bias value that is shown on the left. Another form of neural network is this convolution neural network that performs convolutions with, say, kernels as parameters. Then there are recurrent neural networks that are used mainly for autoregressive predictions in cases where there are, say, time series data. And in such networks, both the input vector at that particular time step, say, for example, t, as well as a hidden state output of the previous time step are given as inputs to generate, say, a particular output. And there are some other types of neural models, for example, transformer models, attention models, graph neural networks that we touch upon later. But these are the, say, fundamental classical ways of modeling, say, neural network architectures, which we will rely heavily on in the rest of the talk. Okay, so now the main advantage of using a deep neural network is that given enough data, it can be tuned to approximate any given function to arbitrary level of precision. And there are several ways to tune the parameters of a neural network, which we don't discuss here, but emphasize the fact that using one of these many strategies to train the parameters of neural network, we can generate, in a sense, a function approximator that can estimate any kind of function and, say, generate estimated samples fairly quickly. Now, this may be any kind of functions, say, including estimating the quality of service or QoS parameters of a Fox system, such as energy consumption, average response time, fraction of, say, violations of the service level objectives, or even, say, operational costs of a hybrid edge cloud setup. So to optimize the resource management decisions in a Fox system, we leverage the strength of neural networks to accurately approximate QoS parameters, that is, they build a neural network-based surrogate model. And these models output are what we use as objective functions for optimizing the decisions of resource management decisions in our setups. Just to recap what Giuliano said, a surrogate model is an approximator which estimates values that are, say, hard to calculate or obtain, for example, energy consumption in a distributed compute setup. And once we have this, we could run either goal-directed gradient-free optimization strategies, such as gradient genetic algorithms, these evolutionary search strategies, or even, say, reinforcement learning. Or we could use some gradient-based optimization schemes that we see that they tend to converge faster than gradient-free methods. Okay, so surrogate modeling has been popular in prior work, and different types of surrogate models have been used in the past. But what makes neural networks special? In the past, as shown on the slide, there are various other methods like support vector machines, Gaussian processes, polynomial models, and so on. However, the main advantage that neural networks provide is that they can be trained to accurately match a given data set, even with systems that dynamically change with time, or even when there are, say, several data sources leading to, say, high dimensional data that requires processing. And these aspects are characteristic to heterogeneous fog environments. And so hence, in recent years, neural networks have gained popularity over these other types of models to act as surrogates for optimizing QoS in fog systems. So let me now present how, using AI or neural networks, we can optimize the quality of service of, say, fog environment using gradient-based approach. On one of the fundamental ideas that we develop as part of our research is called this idea of gradient-based optimization using backpropagation to input, which with this acronym GOBI. And here we use, say, a neural network as a surrogate model. For instance, here we use a fully connected neural network that predicts quality of service objectives for any given state of the fog environment. And we train such a neural network using a supervised learning. We generate data where we can run, say, a random scheduler to cover as much of the state space as possible to create a data set of these XY pairs, where X is the collection of scheduling decisions for each task. The resource utilization of all tasks and the host capacities available. So X is like a state of the system. And Y here is the value of the objective score for this particular state X. And we then trained the surrogate model, say fx theta, where theta is the set of weights of the neural approximator. And we can train this model using, say, the mean square error between the predicted and the true scores. And once such a model is trained, at each scheduling interval, we take the input x and optimize using the gradients of this neural approximator with respect to x using, say, stochastic gradient descent or one of its variant. So just to make sure that this idea is clear of how we use gradients with respect to input, let me just give you a visualization of how the backpropagation of to input idea works. So we send an input x to the neural network and generate a surrogate estimate, let's call it y hat. Then, just like backpropagation to update the parameters of the neural network, we can take the derivative of the surrogate output and use chain rule to propagate the gradients back to the input to identify the specific change in the input required to minimize or maximize the surrogate output. So the forward animation shows the activations of the neurons leading to the neural network output, and the backward animations show how the gradients with respect to the input is calculated. And this complete idea is what we call backpropagation to input, say for calculating gradients, and with this acronym COBE. Before I proceed, are there any questions on this idea? Okay, so let me proceed further. Okay, so now we have seen that neural networks can be used as surrogate models for running various optimization strategies. One of the optimization strategy that I described was this gradient-based optimization, which, for example, using Gobi. But there are again some limitations of these neural networks that Giuliano hinted upon in the previous part. And simply using gradient-based optimization is not sufficient, as these neural network models have this problem that is they tend to saturate, their performance tends to saturate. And this is when, say, feeding more data to the neural model doesn't really improve its performance. Say specifically, as visualized in this figure on the right, which we call as out of distribution data, just means that we need data from settings that the neural network has not seen before. So this graph shows the performance in terms of, say, the accuracy of a deep neural network in predicting quality of service metrics of a fog environment. And as this accuracy saturates, as we continue to increase the amount of data that we give for the same fog setup or for the same fog configuration, as soon as we change the configuration and create some more out of distribution data to train the same model or tune that same model, its performance suddenly shoots up. And this problem particularly is, I would say, imminent in deep neural network models, and further optimization of quality of service in such cases is hard, and more intelligent schemes are required to generate or explore these out of distribution settings. So how do we generate out of distribution data? One way to tackle this problem is to use a simulator, a coupled simulation, couple the, say, a simulated or an analytical model with the physical infrastructure that we have, just to make sure that we can explore these settings that have not been seen before, facilitating generalization to these out of distribution or unseen settings from training time. And specifically, coupled simulation has shown to be promising here, allowing us to run a simulator in the background with the scheduling algorithms to, say, facilitate decision making and inject this additional information regarding the system behavior within the surrogate optimization methods. And a simulator could be used to virtually execute a sequence of decisions and observe, say, how they affect the environment, the tasks, the workloads, and also, say, generate estimates of the objective scores. And through this, an optimum decision of, say, a sequence of decisions may be obtained, or even the traces can enable us to explore these out of distribution configurations, enabling the neural network models or surrogate models to generalize to settings previously unseen. Additionally, simulators can also help us to, say, encode encapsulated knowledge on how a fog system behaves using various analytical models embedded inside simulators, which may be, say, important specifically in surrogate optimization methods to ensure reliability and in settings where they could be arbitrarily, their predictions could be arbitrarily bad based on whether that new data is coming from obscene distribution or not. So simulator additionally allows explainability, interpretability to strengthen vanilla surrogate-based methods. And one way this underlying insight has been used in both industry and academia is through this concept called digital twins. What people have done so far, although in domains other than, say, system optimization, is to utilize digital twins to optimize service-oriented decisions. And these might range from, say, cyber-physical digital twins that are, say, used for optimizing efficiency of supply chains, optimal design and manufacturing of cars, of aeronautical vehicles, drug development, drug discovery, or even, say, space optimization in the context of real estate. Or these might be, say, cyber digital twins, such as the Facebook's metaverse. However, there is still limited use of this insight in performance engineering and resource optimization in distributed computational systems. So to address this gap, we utilize simulators as quote unquote digital twins for the fog environment, just to ensure that we solve the problems that we saw, or ameliorate to some extent the problems that we saw that are akin to these neural network based surrogate optimization methods. And in performance engineering specifically, simulators have gained popularity in the domain of, say, computational systems since time immemorial. Many prior works utilize simulators to either gather data in the form of, say, discrete event simulation traces to train data-driven models. And gathering such data from event-based simulators is much faster compared to actually executing workloads on real systems. And other works have also utilized or leveraged simulators to train and test resource management solutions in, say, a sandbox environment before deploying them in real execution settings. However, recently, the interleaved use of simulators, similar to what Giuliano described, with online optimization methods such as Gobi, has become popular in the form of, say, coupled simulation or co-simulation. So let me answer how exactly this idea of coupled simulation works and what kind of interfacing might be required between the simulation domain and the real environment domain. And in terms of, say, the experimental methodologies or the community that, say, investigates these experimental methodologies, we think in terms of two aspects that are either hardware or software. And hardware can be real hardware, for example, real data centers, cloud systems, or so on and so forth, where each component, say, has a discrete or, say, a disparate physical chunk or physical entity, like CPU, memory, storage, network, etc. Or there could be a model of these that, say, models or emulates these different hardware entities like CPU, RAM, etc. in terms of their, say, performance models, either, say, instruction per clock cycle of or instruction per second of a CPU, or the accesses possible of a RAM, and so on. And the same effects of a real system then can be modeled in a simulated environment. So we have either a real environment or an emulated model of the environment in terms of the system hardware. And similarly, when you go to the software side, or any kind of workload that runs on this hardware, there too are these two types of real software or a model of a software. So real software includes, say, operating system, resource management softwares, or these edge AI applications that we described previously. Or you can create, say, a model of those, say, in terms of the temporal trace of resource utilization of each of these applications that can, quote unquote, mimic the behavior of a software trace in a, say, a real, when we deploy them in a real scenario. So these are two scenarios of real or model of a software. Now, when we think of both hardware and software as real, that kind of experimental methodology is often called in situ experiments or in situ say models, and is very dominant in the industrial world today. And coming to the other extreme where both are modeled, that is when we have both a model of software and model of hardware, this is what we call as a simulation and is extensively used in academic research world. However, when we use both in situ systems and a simulation in that in situ system, we call this coupled simulation or co-simulation. And this is commonly used in resource management settings where we need to manage resources in a real system, wherein akin to a digital twin, we can use a simulator to generate interesting parameters such as quality of service estimates of a future interval beforehand by using this idea of discrete events simulation styles. And this can not only facilitate generating more data for these data hungry models, but also provides a interpretable decision-making platform for, say, out of distribution data generation for robust, adaptive, and long-term performance optimization. So let me now describe more concretely how the idea of co-simulation works, specifically in the context of decision optimization. So a co-simulator simulates an input resource management decision and generates estimates of QoS codes that can be used to feed back to a decision model. And this complete loop usually works in 5 steps. So first, we monitor a real system to generate, say, characteristics such as resource utilization metrics of hosts that characterize the state of the fog computing environment. Second, we send these monitored metrics that we call the state of the system to a decision model, which could be a scheduler, a provisioner that uses either of these surrogate optimization strategies using neural networks, support vector machines, and so on and so forth, and generate candidate resource management decisions to choose from. Third, we send these the system state with the candidate decisions to test to an event-driven simulator that quickly generates, say, quality of service estimates for each of the candidate decisions. Fourth, we send the QoS estimates of the sample decisions from the decision model as a feedback to tune the model and perform online optimization of the parameters of that surrogate model. And fifth, we enact the best decision of the decision model in that physical environment and continue this iteratively in a discrete time control setting. So to seamlessly integrate the two ideas of co-simulation and using these surrogate models, a new interface is required. This is what we believed when we started this research. Hence, we developed this Costco framework, which stands for Coupled Simulation and Container Orchestration Framework, to leverage simulated results to yield, say, better QoS estimates and use them as a feedback to the surrogate models to allow online optimization and say adaptation in dynamic or non-stationary environments. We'll discuss Costco in the next part of the tutorial more, say, extensively, but broadly speaking, Costco is, say, a Python-based framework that uses Docker containers to manage tasks, and all communication is via very standard HTTP REST APIs, allowing it to be very easily extended to other problem domains such as provisioning, management, as well as, say, fault tolerance and things like that. So let me now discuss some use cases, but before that, I'll open for questions. If there are any questions up till this part, feel free to send them on Slack message or unmute yourself. Okay, so let me now discuss some case studies that aim to solve these research problems of resource management in fog environments utilizing the Costco framework. We build on the primitives of co-simulation and surrogate optimization that we described previously to solve several resource management related challenges such as bag of task scheduling, workflow scheduling, and even fault tolerance. So the first use case that I shall describe is based on our paper accepted at IEEE TPDS journal. And this paper extends the idea we discussed earlier of Gobi, wherein we train a neural network as a surrogate model of QoS estimates or QoS metrics of a fog environment, and use this backpropagation to input to run gradient-based optimization in the space of scheduling decisions. And the input of the Gobi approach included only the scheduling decision and other state metrics. And the output that it had to predict was the objective value at the end of the next interval, say. And this is a hard problem. We've seen that there are challenges such as out of distribution data, arbitrarily worse performance in cases or configurations that have not been seen before. So we somehow wanted to inject these co-simulation or the system behavior information inside that model. And as Giuliano described previously, we use a simulator or co-simulated traces to give as a feedback to this neural network that we call Gobi star, and use that to generate more accurate, say, QoS estimates of the environment. So in this extended idea that we call Gobi star, at any instance, say T, we run the Gobi approach to get an estimate of what could be, say, a reasonable scheduling decision. This becomes our candidate scheduling decision choice. And also we predict utilization metrics of the next interval, say, using any analytical model or recurrent neural network such as LSTM. Now that we have the scheduling decision and the utilization metrics, we can run a single step simulation that can give us another estimate of the QoS objective score. Now that we have one estimate of the Gobi surrogate model and one from the co-simulation loop, we can get an idea of whether Gobi over or underestimated the quality of service. And both of these values are fed into an independent surrogate model, which say, which reconciles the errors that the Gobi model had before. And this interactive dynamic between the Gobi method and this co-simulator is what we call as Gobi star. And we conjecture that Gobi star can make more informed predictions of QoS metrics for any interval and hence perform better than Gobi, albeit with slightly higher overheads. So we have two schedulers, namely Gobi, which is based on gradient optimization using neural networks as a surrogate function. And then we extend Gobi model to add these QoS estimates from a co-simulator to further improve its objective scores. And just to corroborate the claim, Gobi star indeed gives, say, a lower objective value compared to Gobi, although it has slightly higher scheduling time, which makes Gobi, say, more suitable for resource constrained servers, but Gobi star more suitable for, say, settings where QoS is critical. So to evaluate the efficacy of the Gobi and Gobi star methods, we use a Microsoft Azure based fog deployment with 10 hosts, and we consider a fog broker and 6 worker nodes at the edge, which are specifically 4 dual core and 2 quad core machines. And in the cloud, we have 4 cloud worker nodes in geographically distant location with 2 quad core and 2 octa core machines. We also consider a similar simulated environment that is scaled 5 times, so with 50 VMs, to test how these algorithms perform in large scale setups. For our baselines, we consider 2 heuristic based approaches, LRMMT and this MADMC, 2 reinforcement learning models, which are this deep Q learning method and this asynchronous advantage actor critic method, and a max weight based scheduler pond and a genetic algorithm policy. And for the simulated environment, the workloads we consider are these workload traces generated from real world bit brain datasets. And for the experiments, we use this popular DFOG benchmarking suite. So these figures show the results comparing the Gobi and Gobi star models with the baselines on this Azure platform with 10 hosts. And as is apparent, both proposed methods are able to outperform the state-of-the-art methods in terms of energy consumption, average response time, and the SLA violation rates. For instance, energy consumption is low because both Gobi and Gobi star methods aim to allocate tasks to a small set of hosts to allow idle hosts to go into hibernation or say low power mode to conserve energy. And these bar graphs with different colors on the right show the performance metrics for energy application for each application type in the default benchmark. And all the gains in the performance are complemented by the low scheduling times of the proposed methods, specifically due to the goal-directed search strategy, gradient-based optimization that we use as part of these Gobi and Gobi star methods. So this is the end of the first idea. I'll take questions now. Okay, so if there are no questions, let me move ahead. Okay, so now that we've discussed this idea of Gobi and Gobi star methods, there is, I would say, a limitation that they have, and that is that they are deterministic neural networks. So fully connected neural networks that take an input X, say of the state of the system, and produce a QoS output Y, that the output of these neural networks are deterministic. However, say in pragmatic settings, systems and workloads are seldom deterministic. And on the other hand, most workloads, they follow very high stochasticity in their behaviors. So even if we generate some sort of an estimate of what would be the behavior of a particular workload in a future time step, that may or may not be true, and there is always some sort of an uncertainty associated with those estimates. And to model this, we extend the Gobi and Gobi star methods to utilize neural networks that generate stochastic outputs. We do this by leveraging this something called natural parameter networks, which is NPNs, where the weights of these neural networks are distributions themselves. And this allows a fairly general, say, mimicking a fairly general distribution types, say an exponential class of distributions like normal distribution, Poisson distribution, and so on. And stacking these different distribution weights one over the other facilitates predicting both an estimate as well as, say, some uncertainty associated with that estimate. And again, the back propagation methods again be extended to propagate the gradients with respect to that with respect to the input from that output layer back to the first layer of the neural network. And the claim is that when we have such kind of an estimate, we can use, say, confidence bounds instead of just the mean values that are estimated to have a more informed decision-making system, and as well as allow that level of uncertainty and that level of, say, prediction performance, that level of confidence in out of distribution settings to further utilize that information to say, improve the quality of service of such systems. And this is shown by these figures here. This new model that uses NPNs, what we call as GAUSH, outperforms even Gobi and Gobi star methods, thanks to the stochastic modeling and improved surrogate estimates. And this translates to lower energy consumption, average response time, and even lower fraction of SLA violation rates. So let me now move on to the next use case, which is workflow scheduling. And by workflows, I mean these scientific workflows that have these precedence constraints, where the fundamental issue is in workflow management is the handling of these constraints, where unlike bag of tasks like workloads, scientific workflow applications can only be scheduled in a particular order. So we need to deploy these workflows, which are again collection of tasks with these directed acyclic graph or DAG type precedence constraints. And an example is shown on the screen for the BLAST workflow. And there are multiple small tasks that are run in a sequence or in parallel with these precedence constraints as shown by these directed edges. Again, similar to a bag of task scheduling, the workflow scheduling problem aims to efficiently map these tasks onto the available resources to optimize quality of service metrics. But now we have an additional constraint that we need to conform to the orders that are imposed by these DAG graphs Okay, so the second idea that I shall discuss today belongs in this area of scheduling these scientific workflows. And a limitation, again, for the Gobi and Gobi star methods that we described previously is that they predict quality of service metrics at the end of the next interval. So they are single step look ahead estimates. However, for say multi-stage applications such as these scientific workflows, uh, such a myopic optimization model may not be helpful. And we might need to run additional simulation steps to make a more informed decision, which we refer to as long horizon policy. And we need to use these multi-step simulation estimates to ensure that the quality of service estimates that I have from the surrogate model are informed by those QoS traces from these co-simulators to allow, say, avoiding local optimas and perform long-term optimization. So to solve this long-term optimization problem, many reinforcement learning methods have been proposed that try to estimate a so-called value function that aims to achieve the same objective of estimating, say, a long-term QoS estimate of any given system state. And to train such a value function, methods have been proposed that use some sort of a bootstrapping approach to use immediate rewards to get a value function estimate for a long-term reward setting. And such methods include, say, temporal difference learning or Monte Carlo learning. But an advantage that Monte Carlo learning provides is that it gives low bias and helps us to generalize and adapt much better in volatile settings. So what we do in a Monte Carlo simulation is to build a tree of system states and say possible actions that we can execute. These actions could be, say, scheduling decisions or migrating tasks, active tasks in the system. And for the current system state, we select a possible action using, say, a balance of exploration and exploitation objectives, which we something referred to as upper confidence bound estimate. And we expand the possible target state. We run several multi-step co-simulations and feed the QoS scores back to the decision model to update its parameters. However, we cannot use a standard RL approach to utilize in this long-term estimate setting. So we build a Monte Carlo learning approach to train a surrogate model that estimates these long-term QoS scores for each single step action using this multi-step co-simulation. And in the case of, say, long-running workflow application, we conjecture that such a long-term optimization model would be helpful to achieve optimal quality of service. So at test time, whenever we are taking these decisions in online, we use these Monte Carlo simulation approach that I described previously to train the surrogate model, and we choose the child node of this tree with the highest QoS estimate rather than having that exploration exploitation. And we continue this in each iteration dynamically to in a discrete time control setting. So these results compare this long horizon approach with the approach that I described previously, which was Gobi. So this approach that I just described is what we call as MCDS, which stands for Monte Carlo Deep Surrogate Models. And we use particle swarm optimization approach, IMPSO, evolutionary strategies, game theoretic model as baselines. And as you can see here, such an approach facilitates enhanced decision making in multi-stage workflows, which gives lower energy consumption, execution time, response time compared to the state-of-the-art methods. And as you can see here, these models outperform the myopic optimization methods as well, which is Gobi. And that is why, see, in scientific workflow applications, it is critical to generate these surrogate models that estimate long-term QoS scores rather than short-term QoS scores. Okay, so up till now, we have discussed several these data-driven deep neural network-based schedulers that outperform classical approaches by providing both scalability, efficiency, and allowing us to dynamically tune them in non-stationary settings. However, these state-of-the-art schedulers typically rely on these advanced gradient-based optimization strategies, or say these Monte Carlo simulations, which could be computationally expensive, which say imply higher scheduling costs. So suppose if we want to generate these scheduling decisions periodically in a broker, very high computational needs would require to have a very beefy broker node in our fork setup. And in non-stage 3 contexts, the most sophisticated schedulers may or may not be required at all times. And in some cases, it might be sufficient to rely on low-cost schedulers, say to temporarily save operational costs. For example, in say a cloud deployment that say computes or provides this Zoom service, it may be possible that at nighttime in a local area, those servers could be maybe switched off or put in hibernation mode or in a low power mode, and say low cost resource management solutions might be deployed there. So recently methods such as this MetaNet method have been proposed that solve this meta problem of dynamically selecting cost optimal scheduling policies. And this MetaNet idea is again a surrogate model that predicts the operational costs and scheduling overheads of a large number of deep neural network-based schedulers, and chooses one on the fly to jointly optimize the scheduling problem as well as the execution costs. So leveraging all these state-of-the-art schedulers in tandem, MetaNet gives all possible benefits of enhanced QoS as well as low cost, as can be seen in the table. So before I move on to the next use case, are there any questions?
Yes, I have a question. Shreshth, can you hear me?
Hi, yes, Hijo.
Can you go back to the MCD? I think it's like a tree structure for yes, this one. Yes.
Okay.
So you use the Monte Carlo simulation to generate a long-term QoS from the root, right? And I want to ask, how many steps do you simulate? So in this picture, you seems like you simulate 4 steps. Is it true?
For this work specifically, I would say that we have this number of steps that we simulate again can be chosen dynamically based on say how confident our model is. If our model is confident enough, we might say simulate only 2 or 3 step lookaheads, or if it is not as confident, we might simulate more intervals. But this again can be a hyperparameter that can be say considered as a constant in settings where we know that these concept drifts are not as often as we might expect. Does that answer?
Okay, thanks. Yes.
Okay, cool. Thanks for the question. Okay, so the next work that I'll discuss is in the area of fault-tolerant computing. And here it is essential to ensure that the fog nodes themselves do not become a point of failure for the running applications. And robust countermeasures are in place to incorporate overloads or failures in fog network or processing nodes. And the problem of developing, say, a robust fault tolerance framework requires us to run appropriate remediation steps. And for such systems to be within the strict specifications of modern industrial demands, they need to be able to resolve diverse kinds of system or network related faults. And this may entail, say, establishing the type of fault at the time of its prediction for, say, more informed recovery decision. Furthermore, to avoid overlooking any fault that may cause, say, significant adverse effects later, and also to avoid overheads of false positive predictions, such prediction models need to be extremely accurate. So again, to tackle this challenge of fault-tolerant computing, we built a novel neural network that we call Pregan, which stands for Preemptive Migration Prediction Generative Adversarial Network. And this was accepted as part of IEEE Infocom this year. And in this work, we target a standard heterogeneous edge computing environment where all of these nodes are in the same virtual local area network or VLAN. And here tasks are again container instances generated from the sensors and actuators communicated via gateway devices. And the edge broker takes all scheduling and management decisions. And we consider system contention type faults. Example of what Giuliano discussed, say in a microservice environment where there might be contentions in that microservice call stack. And these contentions could be of the form of CPU resource, RAM resource, disk, or even network bandwidth. And to proactively prevent fault events in a future interval, we take these preemptive container migration decisions over the active tasks in the system. So this figure visualizes how the complete Pregan pipeline works. So the figure or the grid on the top denotes the intervals at which the Pregan model predicted a fault, and fault is denoted by that black line, and that yellow denotes no fault setting. So these are 200 timestamps, and specifically 38 timestamps are those in which the Pregan model predicted a fault. The heat map or the grid just below shows the fault class prediction for each host, if any. So this is either a CPU fault predicted by the model in red, RAM fault in green, disk fault in blue. So these are CPU, RAM, and disk contentions. And the third grid shows the intervals in which the likelihood score of, say, the predicted preemptive migration decision was better than that of the original decision, say, coming from an underpinning scheduler, either Gobi, MCDS, Gosh, and so on. And the last heat map shows the hosts from which these tasks were migrated. And we observe a very strong correlation between the fault class predictions and the host selection for task migration, thanks to the, again, these co-simulation estimates that I'll describe in a bit. Okay, so Pregan as a method, again, is like a surrogate model that acts as a surrogate of which is a better decision. And it is based on this idea of generative adversarial networks. Just to say briefly recap, these generative adversarial networks have been gaining a lot of attention in the past few years, specifically in the domain of computer vision, particularly say to generate novel images that are not seen in the training data. And these generative adversarial networks, also called GANs, are divided, so to speak, in two networks. First is a generator network, second is this discriminator network. And for any input sample, say if you want to generate a sketch of a bridge, I give a generator what a sketch looks like. I also give it what a bridge looks like, and it generates a sample image of a sketch of a bridge. And then we send that image to a discriminator, which answers whether that new generated image is a good sample or not that we want to generate, and acts as an adversary, telling it to whether it should improve its parameters, how to improve those parameters of that generated network. So both of these network generators and discriminators work in tandem, again, like a game theoretic style, just to make sure that we are able to generate optimal decisions or optimal samples from the distribution that we want to achieve. And this distribution could be, say, the distribution of preemptive migration decisions. And we want to generate samples that are, say, more aligned or more amenable to enhanced QoS than rather not. So that is what this Pregan idea does. And in a similar fashion to GANs, we have these two inputs, which are scheduling decisions from an underpinning decision maker, like a scheduler, like a Gobi model, and also this time series window. So this window is W, which is the state of the edge computing or fog computing environment, for example, through the resource utilization characteristics. And similar to the GAN model that I described previously, Pregan model also has a generator and discriminator network. But additionally, it also has this fault prototype encoder that, in a sense, is just a classifier of what kind of fault there would be in, say, a future interval of the system. And so you can consider that the scheduling decision is a bridge, image of a bridge, and this fault prototype is the image of a sketch. Now I want to generate another scheduling decision, again another bridge image that looks like a sketch, or that looks like a say a scheduling decision that would resolve those faults that this classifier model predicted. So in that sense, the idea of using this generative adversarial network is to create a generator model that generates these new scheduling decisions informed on the scheduling decision input from an underpinning scheduler S, as well as a fault predictor or fault classifier, which is this fault prototype encoder, to generate a more informed scheduling decision using these perturbations in the input, which we call preemptive migrations, and appending it or adding it that to the input schedule and sending that to the discriminator network. Now the discriminator network D would predict me a likelihood score D, which corresponds to which decision is better, either the input schedule or this new schedule that was better. And whichever has a higher likelihood score, that is actually used finally in my discrete time control optimization setting. So let me now describe how we train both of these neural networks. So first, as we described previously, the encoder network, the job of the encoder network is just to classify what kind of faults might occur in a future system state. And this can be trained in a supervised clustering fashion, where we could use an industry-grade contention detection tool in Linux or Windows or these platforms. So a sample of these randomly generated system faults by this fault prototype encoder in Pregan is what is shown on the right. This is a TSNE plot of those prototype vectors or encoded vectors that is shown here. And to train the GAN model, we use a slightly unconventional training style. What we use is we use these co-simulated QoS scores of both these new schedule N, which is after that preemptive migration, as well as the original schedule S. And whichever is better, we generate, say, one hot vector corresponding to that and use that as a supervised signal to train the discriminator network. Now, given any preemptive migration decision and an original schedule S, the discriminator network would be able to identify which is a better schedule and act as an adversary to the generator to train its parameters. And to test this, we run experiments on a cluster of 16 heterogeneous Raspberry Pi edge devices. And for our workloads, again, we consider these DFOG benchmarking suite, which include these edge AI type applications. And we compare against baselines across several metrics, including these fault detection performance, fault diagnosis performance, diagnosis in the sense which host was actually the host where the fault occurred, the overhead ratio, so how much overhead relative to the underlying scheduler did this particular fault tolerance approach have. Improvement ratio, how often was the preemptive migration decision better than the underpinning scheduler in terms of QoS estimates from those co-simulation loops. And finally, again, the quality of service parameters that this system provided. So these are the results corresponding to some of the state-of-the-art methods, which include this DFTM based on integer linear programming, ECLB and PCFT, which use evolutionary optimization strategies, and the CMODLB, which is very similar to the prototype encoder that we had before, but now it does classification or clustering, uses k-mean clustering to detect and classify faults, and then use that as a prior to update the scheduling decision using something called particles form optimization. And these results compare, say, the detection and diagnosis, as well as the fault classification performance of Pregan against these methods. And clearly, Pregan method has the highest detection and diagnosis scores, including the improvement ratio, with lower overheads compared to the best baseline with respect to the detection accuracy or detection F1 scores. So the high detection and classification accuracies of Pregan, again, also translate to higher QoS scores. So this gives additionally 8% lower energy consumption, 5% lower response times, 12% lower SLO violations. It is able to correctly identify faults and give higher classification accuracies. And it is able to achieve all of this with 24% lower overheads compared to the baseline method, just because now we have this discrete event simulations going on that can be performed fairly quickly to train our model and adapt it on the fly for non-stationary settings. So this makes Pregan one of an ideal choices for reliable edge computing with time critical applications. So let me take a break here. Do you have any questions? If there are no questions, let me proceed. Okay, so the next work that I'll discuss, or the use case, is this area of reactive service resilience. So what we've seen up till now is this Pregan method, which is proactive fault tolerance. But again, just because these are not completely accurate, the F1 scores are not 1, or the accuracy numbers are not 100%. So it is possible that there are false positives, false negatives that these Pregan methods, proactive resilience methods provide. So how do you reactively solve these challenges? How do you reactively make sure that even if there is, say, a contention, even if there is contention related failures, either a fog broker or a fog worker fails, what happens then? How do you make sure that it does not affect the service? It does not lead to very high service downtimes, and we maintain the quality of service that we want to achieve. And as typically fog nodes or fog environments have this broker worker distinction, broker worker architecture. In case of a worker failure, we can simply use another worker as a redundancy and reinitialize the jobs that were allocated to the failed worker to ensure that our service downtime is as low as possible. However, if a broker fails, it renders the complete federation or complete group of workers that it is handling useless. And so what is, I would say, critical in terms of service resilience in fog architectures is this idea of broker resilience, as worker resilience is something that is less challenging compared to this. So this idea is based on what I'll describe. This work is based on a paper accepted at IEEE DSA. And what we do is we build confidence-aware surrogate models. So the figure shows how, say, if a particular broker node fails, for example, the one marked in red, we can have, say, multiple perturbation types to update the topology graph of the fog system. And we call each of these perturbations to the topology graph as node shifts in the rest of the this use case discussion. And this surrogate model, again, based on the say node shift operations and an input fog topology graph, generates a QoS estimate and a confidence score of these perturbations and selects the one that would, say, minimize or ameliorate to the maximum extent the QoS adverse effects of the QoS through these failures of the fog nodes. So to model this, there have been several approaches developed in the past in the area of neural network design. And one such approach is called graph neural networks. What this allows us is to utilize the topology as a graph, of the fog topology as a graph. That might, say, include the key performance indicators of each service or each host node, such as utilization characteristics. And we can then forward this graph to a neural network model, such as graph convolution neural network or a graph attention neural network. And these allow us to generate dense latent representations as shown on the right that could then be processed by downstream predictors, such as fully connected networks or traditional deep learning models. So to find the best node shift that I described previously, we develop a model that we called CARL, that stands for Confidence Aware Resilience Model. And it takes as inputs the metric of the system, which is the state of the system, a particular, say, task scheduling decision from an underpinning scheduler like Gobi, MCDS, and so on, and the graph topology. And outputs, say, a confidence score for the input pair or input tuple. And this confidence score is to learn using the same model as we did in Pregan. That is, for any two input topology graphs, we give a score of 1 to the decision that has higher QA score and 0 to the other. And using this idea of backpropagation to input, we generate these performance metrics. And the main reason we use this is to make sure that we do not fine tune in every step. So whenever there is some sort of a contention in the system, possibility of a contention, just because these CARL methods or these resource management methods are running on the brokers, we do not want in already say a contended or say overutilized state, we want to ensure that the resource management models itself do not impose significant overheads. And one of the major components of these overheads that could say give rise to large overheads is this periodic fine-tuning. And this fine-tuning could be either of the analytical methods or co-simulation methods, or even of the surrogate models. So we want to have not just a QoS score, but we also want to have just to make sure resilience is there, just to make sure that these already overperforming these fog brokers are not imposed with additional overheads. We want to reduce the number of times that we tune these surrogate models. And to do that, we have these performance metrics as well as confidence scores. And similar to the Gobi and MCDS methods, we can utilize the performance metrics such as QoS estimates to optimize the topology of the edge federation, that is to find out what is the optimal node shift operation. And we can use these confidence scores to decide when to fine tune the surrogate model. So to calculate these thresholds, we use these popular extreme value thresholding techniques such as peak over threshold. And as shown on the left, the model is trained only when the confidence score drops below this threshold. And as soon as we train the model, the confidence scores shoot back up. And the advantage of using such a mechanism is that we do not need to fine tune the surrogate model in each scheduling interval, further reducing the chances of contention, further making sure that these models itself make sure that these models itself do not give rise to faults, and further make sure that the computing system itself is resilient to faults. So experiments on a similar test bed as Pregan, we see that CARL method is able to give improved QoS scores compared to the state-of-the-art methods. So here we use this step GAN approach, which is again a GAN style approach for fault remediation. Similarly, we have TOPOMAD, FRAS, and LBOS. These are again evolutionary strategies. ELBS is very similar to the particle swarm optimization approach. And similarly, diverse and ECLB are again evolutionary strategies using contemporary models such as heteroscedastic Gaussian processes and things like that. So this was the last case study that I wanted to discuss as part of this subsection of the tutorial. And in the next half, we'll discuss, we'll have a more in-depth discussion of the Costco framework. I'll describe how to install and set it up. And say we shall implement a very basic co-simulation and AI-based task scheduler in Costco. And we'll test it both in a simulated environment and a Microsoft Azure-based cloud computing setup. And then we shall conclude with elementary discussion of how these methods can be extended for future research. So I'll stop here for questions. Otherwise, we'll take a short break of 15 minutes. Any questions on the last part?
I would suggest we take a break of 5 minutes in the interest of time. So instead of 15,
okay, sure.
So we can reconvene at 1 past so in 5 minutes.
Thanks everyone for joining back. So I shall now resume the tutorial, and this part of the tutorial will demonstrate and discuss say a hands-on component of how to leverage all of these ideas that we discussed before of using AI and coupled simulation in actually implementing these kind of a scheduler or these fault tolerance policies or these Monte Carlo simulations in what we call the Costco framework that allows us to efficiently and autonomously integrate various ideas by providing these primitives beforehand and enabling, say, implementation time reduction to far more extent compared to other frameworks that are out there. But before I proceed, I have shared some links on the Slack channel that you might find helpful, and particularly the one that is the second one, the Gitpod demo. That is what we will use today. So before we proceed, for those who want to get a more hands-on idea of how to use these schedulers in Costco, please feel free to open this link, and it will run some initializations. If you face any problems, please tell us. And also during the rest of the presentation, feel free to interject at any point in time to ask questions. Let me show you how to set up the framework. So we will utilize this Gitpod service. This is like a free container service that allows you to have a, say, operating system independent setup without setting up the Costco framework itself on your local machine. You can just test out various schedulers. You can implement things on the fly by providing this virtualized environment in a Gitpod container. So all those who do not have access to Slack on the machine at which they are, for example, Zoom machine, then just Google Costco Imperial, and hopefully the first link that should show up is this GitHub repository. So this GitHub repository contains all the code fragments, data sets, as well as the initialization scripts that are required for running the Costco framework and testing it out on Gitpod. So once you have this up and running, just make sure that you click this Open in Gitpod button. And feel free to give it a star if you use this project. So when you start a Gitpod page, it should ask you for your GitHub credentials. Just put them in and it should create a container. It should start a container that looks something like this. So this is like a Visual Studio interface, Visual Studio Code interface, and it should automatically start initializing the container, installing various applications and dependencies for the Costco framework. And this takes around 5 to 10 minutes. So I'll resume the slides before we get back to this. If you face any issues, I'll wait for a few minutes, a minute or two to take any doubts or questions if you're having any issues in logging in or running the Gitpod service. Okay, so if there are no questions, let me get back. Okay, so this hands-on part is actually divided into 6 chapters. In the first chapter, we'll discuss what the Costco framework is, how it works, what all functionalities it provides, what all features it provides, both primitives in the sense of the interface between surrogate models, co-simulation features, and so on and so forth. We will also discuss the implementation details of the Costco framework, touching upon the code structure and various modules provided in the code. We will discuss how to use the framework, say how to execute, say an existing scheduler that is implemented in Costco, or even write your own custom scheduler, how to run that in a simulated environment, how to run that in a say Microsoft Azure based cloud setup, or even any other say even a say Raspberry Pi based edge cluster, so to speak. So let me start discussion of the implementation. So just to recap, Costco is a Python-based framework that allows orchestration of Docker containers in both simulated and real distributed computing environments. Costco uses the assumption of the system model that the execution runs, say, on a bounded time scale, with the timeline divided into these discrete chunks that I mentioned previously, that are of fixed length, which are called the scheduling intervals. And all the workload creation, decision making, execution of tasks, migration, etc., are all run at the start of the scheduling interval, just to make sure that we are in that discrete time control setting. So all of these controllers like scheduler, workload generator, all of these are discrete time controllers. Okay, so to implement Costco, we use this object-oriented programming model to realize its components using the Python programming language. And I'll just provide some details on the important classes that would be critical later on. So the first and foremost is this host class that creates or simulates using this data center class, which provides a list of host objects in the simulator or a physical environment or a framework. And then we have the workloads, which are like either time series models of these resource utilization characteristics, such as instructions per second, RAM, disk, etc. Or these are actual Docker container images as part of physical experiments. Then we have the scheduler class, which has two critical functions. One is the get, the selection function, and one is the placement function. Selection function actually selects these different, I would say, containers or simulated containers or simulated tasks that need to be scheduled or need to be migrated. And placement function for the selected task generates the target hosts that these selected tasks need to be scheduled or migrated to. Next, we have this host class, which monitors and manages these simulated or physical hosts. And this contains models of IPS, RAM, disk, and network bandwidth. To get the power model, so power consumption of the host, instead of measuring the power intake by using a separate sensor, we use these power consumption models. So these are functions or mappings from CPU utilization to power estimates. So that is what is part of the power model. Next, we have this task class, which manages the task or containers that are under execution. For the framework, we have two more classes, server and the agent class. And the server resides at the fork broker. So this is the say HTTP server that or the Flask server, Python Flask server that sends requests to these fork worker nodes, and the agent class executes these commands that were or applications that were sent by the fork broker. And then we have this framework class that contains all the implementation of, say, integration in terms of co-simulation estimates, surrogate optimization, these checkpoint restoring of these containers, migration of these containers, preemptive or non-preemptive migration, and so on and so forth. And the simulator class provides very similar functions as that of the framework class, but now in a simulated setup. And finally, we have this auxiliary helper class called stats that contains logs of the utilization metrics of hosts and workloads, QoS scores, energy consumption, things like that. That act as a, say, a feedback loop to interface between framework and simulator. So let me now quickly get back to that Gitpod service just to make sure everybody was able to set up that service. So this is something what you should be able to see. If there are any discrepancies, please let me know. You can close down any notifications. Okay, so if there are no discrepancies, I believe anybody who is performing hands-on can see something like this. Then let me get back to the slides. Okay, so let me now introduce how to implement your own custom scheduler in Costco. So for this tutorial, we will extend a very simple scheduler from CCP 2012 paper, where the host is selected from threshold policy, wherever say CPU utilization is greater than 70%, we select these hosts. And from these selected hosts, we select the container or the task that has the maximum CPU utilization of that within that host. And for these selected containers, the target host selection is usually say random. And the idea behind using this kind of a scheduling policy is just to make sure that we are balancing the load across different host machines. However, we leverage this idea of co-simulation to improve this. So instead of selecting the target hosts randomly, we co-simulate all possible container to host allocations and pick the one with the least energy consumption as our QoS code. So this is the code that that we will follow. Let me describe it in more detail by implementing it here. So all those who have this Git pod service running, you should be able to see some files on the left. Say if you select main.py, that main.py file should be open on similar to a IDE. You should see the main.py file here, and also a terminal window just to run commands here. So the structure that I described previously, all of the classes are within their respective folders. So framework class, scheduler class, stats class, and so on and so forth. So what the particular class that we will be extending is within the scheduler. You can see that there are already many schedulers that have already been implemented, like Gobi, Gobi star, the spawned approach, the baseline approaches, and so on and so forth. And all of these extend, say, suppose if I open the Gobi file, it extends the scheduler class implementation. So this provides some boilerplate templates that allow us to say, integrate or collectively utilize the functionalities provided by the other class methods, such as frameworks, framework class, simulator class, stats class, and so on and so forth. So to create a new scheduler, custom scheduler, let me get back. Let me get back and just quickly say explain how we integrate different components, the selection and placement functions. Give me a second. Okay, so we have those selection and placement components that we want to implement as part of a scheduler. So let me start creating a new file here. Let me call it simple scheduler, both as capital .py. So to implement this, first I will just because we need to extend the scheduler class, what I will do is that I will import the definitions from that class. Then I will import the another helper library that allows us to perform some argmax kind of operations. And similarly, just like a simple Python class implementation, I will start a simple scheduler class. I will add the parent class name, scheduler class. I will create an init function. I will call the init function of the parent. I will define the two selection placement function. Pass is actually a no-op operation, which is just a placeholder. So to implement the selection function, let me start with an empty list of empty container IDs. So container IDs are identifiers of the containers that I want to select. Initially, this would be empty. So Then I will iterate through the host IDs in the host list. So in the framework class, which is the environment class, there would be a host list that is like a pointer to the list of host objects that store all of this information of hosts, such as resource utilization characteristics, what kind of containers they include, and so on and so forth. Let me also share this particular code just to make sure people who are having difficulty in following. I'll share this in the Slack channel. Okay, so this is my host list of the environment class. And if my host, the CPU utilization of the host is greater than 70, so get CPU returns my CPU utilization percentage, I will first find out what are the identifiers of the containers that are residing in this host. So containers that are allocated and are active in this host. So for that, I will again call an environment class function, which is get containers of host, and I will provide this host ID. And only if my container IDs list is non-empty, then I will find out the IPS, which is the instructions per second for each of these containers. So for what that I will do is I will go to the container list. I will find out the pointer to the specific container object using this container identifier, CID, and I will call the base IPS function, which returns me the instructions per second for that container. And I will loop this for all the container IDs that I have within that host. Now, I need to select that particular container ID corresponding to the maximum instructions per second, which is again maximum CPU utilization. So what I will do is that I will append to the selected container IDs list the container ID that corresponds to argmax of my container IPS list. So container ID is np.argmax container IPS. And this would iterate over all containers. This would iterate over all hosts. So I can just return selected container IDs as part of this function. So this was fairly straightforward. No co-simulation, no nifty ideas involved here. Now in the placement function, what we wanted to do is we want to use co-simulation rather than say allocating these selected containers randomly to balance load. We want to intelligently map these say overutilizing containers to those hosts such that our number of active hosts in the system can be minimized. By number of active hosts, I mean number of hosts which have at least one container allocated. Just because Microsoft Azure and various cloud platforms, even these edge devices, fog devices, whenever they don't have any load on them, they typically go into a low power mode, hibernation mode to conserve energy. So we want that the number of active systems are maximized just to ensure that the hibernating systems are maximized. So again, I will start with an empty decision list, and decision again is a list of ordered pairs of container identifiers and host identifiers. So I will iterate through the container list, the IDs, container IDs that I have. Let me rename this to container IDs just for understanding. And I will generate these codes. So the stats class that I described previously, that provides me a helper function that for any given decision, I can independently test what a QoS score would be for that decision. And what I will do is that I will call that stats class, the function run simple simulation of that class, and I will give a decision, a sample decision with only a single schedule, which is a singleton set of CID comma host ID. And I will get the energy consumption from there. And I will iterate this over the complete host list. So what this will give me is list of QoS codes, energy estimates for each possible target host allocation for the given container list. And I will append the ordered pair of the container identifier and the host identifier, where my host identifier corresponds to the host with the minimum energy, the minimum energy consumption, estimated energy consumption. And finally, I will return. This iterates through all the containers that were selected. I will return my decision list. So let me know if there are any doubts, any questions. If not, I'll move on to the slides. You should have now a simple scheduler.py file inside the scheduler folder, which has this definition of the simple scheduler class. And to test this custom scheduler, we shall work with a setup with 50 simulated cloud VMs and shall use these BitBrain workloads. All of these are already implemented, integrated with the Costco framework. And these BitBrain workloads are actually real traces of resource utilization metrics from some 1500 odd VMs that are in BitBrain distributed data center. And these are generated from industry applications, including analytical programs from banks, credit operators, insurers, and so on and so forth. So we will use these benchmarking for our benchmarking in our simulated testbed. And to integrate the custom scheduler in the Costco framework, the new file that we added, let me go back. To the main.py file. So here you can see all the imports, including the scheduler imports. We will add another line here. So from scheduler, simple scheduler, import simple scheduler. Let me, so here there are some global constants in the sense that number of time steps that I want to simulate. So let me change this to say 20 for now. Number of hosts that I want to simulate, let me say change it to 10 hosts. Interval duration. So each scheduling interval is how many seconds long. This could be arbitrarily low, 1 second, or very high, say an hour. But for now, let's keep it to say 300 seconds, which is 5 minutes. And then in the initialize function, there are different kinds of workloads that can be initialized, different kind of schedulers, environments, and so on and so forth. But for now, let me change this to simple scheduler. And that's it. I'll just run Python 3 main.py. This should take a few seconds to run an event-driven simulator rather than actually executing 300 seconds times 10 intervals. So 50 minutes. It should be done fairly quickly. So this is downloading the BitBrain dataset. And don't worry, we'll share these slides as PDFs in the Slack channel as soon as this tutorial is over, just to make sure you can go back to them. Sorry, I think there's a typo. Anybody who is facing any issues in getting up till here, feel free to unmute yourself. Okay, so this is now running a discrete event simulation for 20 intervals, 0 to 19. And this generates several logs in the form of data sets of metrics, host utilization, CPU utilization, and these logs can then be used for training, say, a surrogate model. So for example, if I consider something like CPU utilization with interval, or number of containers with intervals, so host 0 has some containers, host 1 has some containers, host 8 and host 9 have containers. And you can see clearly that out of 10 hosts, only 3 or 4 hosts are active at a time. At a time, probably only 3. So this gives us an idea that it is trying to minimize the number of active hosts in the system in order to ensure that rather than randomly allocating these overutilization containers, it is allocating effectively to those hosts such that the number of active hosts are minimized, and we can make sure that other 7 hosts are in low power mode, which is again something that a feature of Costco that it simulates, which can reduce energy consumption of a real physical test bed. Also, there are some other metrics, say in the sense of number of migrations performed, total energy, etc., and CSVs that you can utilize for your own research. Let me now quickly go back to the slides. Okay, so now the hands-on component is complete. Feel free to watch rest of the demo from here onwards. So let me now give you some details on how this custom scheduler was actually working. So as I described previously, a scheduler is divided into 2 functions. One is the selection function, and there is the placement function. And the selection function selects the container instances that should be scheduled or migrated. And the placement function chooses for each selected container or task where it should be migrated to. So in Costco, we assume that each new task in the system is allocated to a dummy host as soon as it enters the system. And this dummy host doesn't actually execute this task. However, in a sense, it has a CPU capacity of 0 instructions per second. But what this allows is to consider each task as now, each decision as a migration decision, instead of considering both scheduling and migration decision together. And this allows us to integrate both simulators and simulation and framework environments, making it simple for, say, researchers to extend this with their own algorithms. So in terms of the selection function, what we did was we first initialized an empty list. We found out the active containers in that host. We found out the host machine that was actually had CPU utilization greater than 70%. We iterated over the containers within that host. We selected the container with the highest instructions per second, and we returned the selected container IDs, identifiers, as part of the output of the selection function. For the placement function, we iterate through the selected containers, and for each selected container, we simulate all possible allocations to the hosts in the system. And to do this, we use the run simple simulation function that is implemented as part of the stats.py class. And finally, we select the migration decision that corresponds to the one with the lowest energy consumption. So on the right is the stats.py file that has an implementation of this simple single-step simulation function. So similarly, we can also quickly go through the Govi scheduler that uses a neural network as a surrogate model to optimize the scheduling decisions. Firstly, here we have both operations of container selection and placement being performed by the placement function. And within this function, we get the latest system characteristics that define the state of the system. We run this gradient-based optimization and return the converged scheduling decision as the output of this function. Similarly, we can also extend the Gobi scheduler to say perform long-term QoS estimation in the form of Monte Carlo simulations. So as we discussed earlier, and this allows us to also be effective when in terms of long horizon planning, when the workloads that are there in the system are in the form of these directed acyclic graphs or scientific workflows, and long-term QoS estimation is required to avoid, say, myopic optimization. Okay, so let me now discuss how to test the implemented scheduler on a real cloud test setup. So for this tutorial, we will consider a cloud environment of Microsoft Azure VMs. There are 6 VMs that are present in the UK South location, where this broker node is present, and 4 VMs are present in the East US location. Our resource management solution is run in this Git pod container, which has been initialized probably in the Git pod container service that is in London. And for workloads, we use again this DFOG benchmarking suite. We consider 3 workloads as containers. The you only look once YOLO deep learning based object detection. The Pocket Sphinx is a natural language processing based speech to text application. And ANSYS is again a text to audio synchronization tool. So all of these are edge AI applications that we started with to motivate fog applications. So we deploy using the Azure dashboard VMs and install this Costco framework using, say, various ways that can be installed. So for one of the easiest ways to install the Costco framework on these VMs is via that xOpera deployment tool. So that is a CI/CD tool for automated deployment of say any software package, including Costco, which integrates various Ansible scripts to automatically deploy various Flask service plugins and these framework simulations interfaces that the Costco provides automatically. So once we have these VMs set up, we can simply run this xOpera command that installs all the required packages in these different worker nodes to execute our say any experiment. Okay, so if you have a setup ready, and if you have the scheduler that you want to implement as part of your research ready, then it is fairly straightforward to run it on this fog deployment. Let me go back to the code. So what Costco provides is automated installation of these different software packages in the worker nodes, which I've already completed. And if you want to say specify in your own VLAN setting, what are the specific IP addresses of each of these worker nodes, you can go into the framework folder. In the config folder, there is this VLAN config.json file, which specifies the IP address, the number of CPUs, and the power models that we want to utilize for each of these hosts. So Costco already has several power models available. For example, the B2S machine of Microsoft Azure uses this B2S power model. Similarly, an EC2 machine would have a PM EC2 power model implemented as part of Costco. So what I will do here is that the Azure dashboard that I had shown previously, I will update this JSON file with the IP addresses of the worker nodes that I have in my Microsoft Azure dashboard. So I've updated these IP addresses. I will use the same scheduler function or scheduler class implementation. Costco allows the same implementation of schedulers to be integrated both in simulation environment as well as physical environment. You do not need to make any alterations at all. The only thing that I will change here, just in the interest of time, is to reduce the number of simulation steps, and I will put an interval time of 30 seconds. And then Python 3 main.py, my environment. I'll specify my environment using this -e flag, which is this virtual LAN environment. And the mode of execution could be either 0, 1, 2, 3. 0 is for also installing the Costco software packages on the worker nodes. One is only installing software packages, 2 is only executing the workloads, and 3 is deleting the software packages. So for now, I will only execute the workloads as I've already installed the packages there. So to integrate all of these different resource utilization metrics, Costco uses the InfluxDB service. So this is a very lightweight database just to make sure that we have time-stamped information, time series information of the resource utilization characteristics, and we are able to save those to perform any kind of surrogate optimization or neural network training. Okay, so first it obtains host information. Host information is in the form of, say, resource utilization capacities. Say what is the maximum RAM, what is the maximum disk bandwidth, what is the maximum storage, what is the maximum instructions per second that a particular host provides. This is just to make sure that we are able to calculate the percentage utilization that we use as part of Gobi and other methods. And all of this is done through Ansible scripts, just to make sure that it is automated, parallelized, and there is some sort of robustness in the system in terms of any command that is executed in one host is also executed in any other host. So, okay, so here we see for each IP address, we have a total memory in megabytes, disk, bandwidth, the number of clock seconds it took to generate to execute a sysbench benchmark. And we know that that sysbench benchmark has some static instructions. So we can find out what is the instructions per second using that benchmark, read speeds, write speeds, and so on and so forth. And then so it has in the first interval, again, as I said, it is a discrete time control problem. In the first interval, it generated this YOLO container as an application, and it allocated to the 202 IP address worker node. It collected the resource utilization metrics. And as you can see in the first VM, there is a container. The VMs are idle for now. Similarly, in the second interval, a Pocket Sphinx container was created, which was allocated again to the same host. And as you can see here, the number of containers in that host has increased from 1 to 2. All containers are active in the system. And host allocation for the first 2 containers is 0, which means the first VM. It created another Pocket Sphinx container. And here you can see that now it is migrating, checkpointing a container, the second container that was created. It is migrating that container to another IP, which is 157, and restoring that container on that IP address. So it is performing both scheduling of new tasks as well as migration of active tasks in the system. Again, a new workload of YOLO Docker container was created. And you can see here now in 7th VM, there is a migrated container active in that system. Another migration step performed here. In this, at this time step, at this interval, 2 new containers were created, ANSYS and Pocket Sphinx. And the Pocket Sphinx container that was created second actually completed execution, so that was deleted from the system. And whatever resource utilization metrics and the response time, etc., those were logged in that InfluxDB service. Another migration here of, okay, so there are 2 migrations being performed here. One is of the ANSYS container, another is of the Pocket Sphinx container. And these might be arbitrarily large containers. So suppose if you checkpoint a container, migrating that might take a few seconds, maybe a minute or so. So there can be policies implemented that also consider migration time as an input or a signal to take an informed decision in terms of which migration is, say, better or has lower overheads compared to other migration decisions. And that can also be used to jointly optimize both energy consumption or other QoS metrics with the overheads in terms of migrations. So let me get back to this in a bit. This would take again a few seconds to complete. Let me continue with the slides. Okay, so the overall goal of the tutorial was to say, illustrate performance engineering challenges faced by researchers when integrating say, AI and co-simulation based methods for optimizing the quality of service of Fox systems. And we gave an overview of the state-of-the-art AI methods, the techniques that utilize surrogate models, and how to improve them, how to solve various challenges that surrogate models present, such as the data saturation problem that we described earlier, using these co-simulation tools, co-simulators being akin to a digital twin, acting as additional media to generate data for data-hungry neural networks, as well as out-of-distribution data configurations to solve some of the challenges such as data saturation. And all of this combined interleaved optimization using surrogate methods as well as this co-simulation loops facilitates enhanced quality of service, especially in time-critical applications where the workload dynamics and the host dynamics are non-stationary, and allowing them to be, say, adapting them quickly to ensure minimum violations of this service level objectives that are defined by the users. And a particular focus of this last part was how to deploy these different schedulers, these different resource management policies using the Costco framework, where the Costco framework provides several primitives, such as the simulation steps, allowing this to integrate, say, a surrogate model using this simulated estimates to provide a more informed decision of what would happen in a future system state, and take enhanced decisions specifically in dynamic settings where quality of service is, or these performance indicators are something that are critical for both in terms of cost, in terms of energy consumption for the end user as well as the service provider. So let me now get back to that and give you some very briefly some ideas on how to extend both of these together. So another container was created in the last scheduling interval. Okay, so this was the last interval that has completed execution, and it is now generating some logs correspond similar to what we had before. So this allows us to use the same mechanisms for data pre-processing for both simulated data as well as the data generated from physical setups. And you can see here that the metrics again are, just because this was fairly short execution trace, the metrics have been saved here. And in terms of host allocations, again, we try to minimize the number of active hosts in the system. So at max, maybe 1 or 2 hosts are active at a time, just to ensure that the number of low power or hibernating hosts are maximum to conserve energy. So now this opens, say, discussion for various other problems that are being trying to, at least at Imperial, we're trying to solve. on how to say leverage both of these in tandem, how to utilize these simulated estimates. What if these simulated estimates are itself biased because of some exposure or some expert labeling errors, how to tune those parameters both dynamically or in static manner, as well as feed these additional informed decisions to say surrogate models for these cross say resource management type classes to have a joint optimization in not only the scheduling or fault tolerance, but also say resource provisioning and etc. And how say scheduling decisions could inform the provisioning models, decision models, to take a more informed decision in terms of what kind of scheduling policies are applicable for a particular provisioning decision, and use that for performing a holistic optimization of fog environments, both using AI and co-simulation. So thank you for your kind attention. I hope this course helped you understand the basics of fog computing and gave you some confidence on using AI and co-simulation strategies, specifically in the Costco framework for your own research. If you have any questions, we are open now, or feel free to send me an email in case of any queries.
Okay, so if there are no questions, we thank you very much for attending this tutorial. And as Shreshth said, feel free to reach out to us if you want to ask questions or engage with us on this Costco platform. Thank you very much to everyone for attending. Have a good rest of the day. Bye.